In our final podcast in the series Ionic Compounds, we're going to talk about how to name and write formulas for ionic compounds that have polyatomic ions. Breaking down what the heck a polyatomic ion is: poly, many, atoms, ions, charge. Okay, so what we're talking about when we say polyatomic ions is we're talking about a group of atoms with an overall charge that act as a single unit. So up until this point, we've really talked about a single metal or a single nonmetal. Now we're going to talk about groups of atoms that function as a single unit with a single charge. This is a list, but it does not include all of the polyatomic ions. These are the polyatomic ions that you will have on your chem data sheet that you will be able to reference. These are the ones we'll most frequently use in this class that you'll come across, but by all means, it is not an exhaustive list of all the polyatomic ions that are out there. I'm going to tell you the best thing you're ever going to hear in this series of podcasts, and that is you do not have to memorize these. You do have to know how to write formulas and how to name with them and how to use your chem data sheet. For ionic compounds that include polyatomic ions, we're following all the same rules as before. We're naming the representative metal as is, just give the name. For a transition metal, we're giving the name and the Roman numeral. The only difference when you're dealing with a polyatomic ion, so those rules still follow, is for the polyatomic ion. So keep those rules in mind. We're just talking about what to do with that polyatomic ion, which is a nonmetal. So we name these polyatomic ions as is. Take the name straight off the list, don't change the ending, keep it as is. A couple things to notice from the list is you may see something that says like hydrogen carbonate or bicarbonate. That is part of the name. You just give it as the name as is off the sheet. We're also going to just spend a quick moment talking about oxoanions, and these are polyatomic ions that have oxygen, and I'm going to point out some of the patterns that they have for the charges and the naming, but for the most part we're going to see the terms ATE at the end of polyatomic ions that have more oxygen and ITE at the end of polyatomic ions with fewer oxygen. So here are some examples of base names for polyatomic ions. We have acetate, carbonate, hydroxide, nitrate. Most of these are 8 ions. Most of them are also negatively charged. The exception to that is going to be ammonium, which does have a positive charge. You do treat it like a cation. It does get to go first. It is still an ionic compound. It is the odd duck out. So we're going to kind of ignore it for now, but we will see that again. Just know that ammonium is positive and it doesn't follow a lot of the other little rules that we have for oxoanions. So notice that each of these given, except for ammonium, has an 8 ending in it, except for hydroxide, has oxygen in it. These are our oxoanions. These are the base names for them, and base names is important. All right, let's look at a couple patterns in charges and the number of oxygens. So the polyatomic ions, the 8 groups that are in purple, are the ones you're going to come in most contact with throughout this class. Just kind of included the other ones for some pattern purposes. But let's start in this upper left-hand corner. If you can remember in the boron family that you have 3 oxygens and a -3 charge, working your way across carbon family, nitrogen family, there's 3 oxygens for each of the base 8s. And the charges decrease 3, 2, 1. So we have some patterns working across, starting with phosphate, starting with phosphorus, and then sulfur, and then chlorine. Okay, we see the same pattern for the charges, -3, -2, -1. And the oxygens are the same except for chlorate, because chlorate just totally messed up the pattern. And I would never speak in absolutes in chemistry. There's always, always, always an exception to the rule. Can I get an amen?
Amen.
All right, let's look at some patterns in naming for these oxoanions. So starting with our base name, the 8 ion is your base name. So we have here in our example, this is our stem, chlor, for chlorine. and our base 8 is ClO3 with a -1 charge. We just give that the 8 ending chlorate. If you have your 8 ions, your base 8 chlorate, but you add an additional oxygen, it's going to have the same charge, but you're going to put a PER prefix in front. So, for example, ClO4 is perchlorate, so it's the base with an extra oxygen. If we take our 8 ion and we subtract an oxygen, so instead of ClO3, it's ClO2, okay, we're going to change the ending to ite. Remember a couple slides ago we said 8 is more oxygens, ite is less. So ClO2 would be chlorite. And finally, if we have our original base 8 ion chlorate and we take away 2 oxygens, again, the charge is the same for all of these, but we're going to put a hypo prefix along with our ite suffix. So both the ites are showing a decrease in oxygen. ClO1, or it'd be 2 less than the original base, would be hypochlorite. Now, I'm telling you this not because you need to memorize this, but because you're going to come in contact with a lot of different oxo anions that follow this naming scheme, and I'd like you to at least understand where it came from. Let's talk about how to write those formulas. You're going to find the charge of the representative metal or the transition metal and the polyatomic ion. And remember that the sum of the charges has to equal 0. So we can still do our drop and swap. We just want to mathematically double check that the overall positive charge cancels the overall negative charge. If we have more than one polyatomic ion, so anytime you're writing a subscript of 2 or more, you need to use parentheses. Here's an example. Hydroxide is OH. If I want to say 2 hydroxides or 3 hydroxides, I can't write it OH3 because that says I have an oxygen with 3 hydrogens. You break chemistry. No, you have to say OH. I have 3 of this entire unit. Remember, it's acting as a single unit. Let's practice. Hydrogen sulfate. So hydrogen is my cation, even though it's not a metal. Just go with it. That's a +1 charge. It's in group 1A. It's acting as the cation sulfate. Ooh, that's a base 8 oxo anion. Looking at our chart, that is SO4 with a -2 charge. We have a +1 charge. We have a -2 charge. We're going to take those charges, we're going to drop them, and we're going to swap them. Okay. I don't need to write the 1, and because it's only 1, I will not use parentheses. I have 2 hydrogens for every 1 sulfate. That's what this is saying. If I accidentally write the parentheses, that's okay. That's not going to hurt me. But let's double check our charges. We have 2 +1 charges for an overall +2 charge on the cation. And I have 1 -2 charge for sulfate on my anion. Those add up to 0. Excellent. I've done it well. Right correctly. Bad grammar. Moving on. Next example is aluminum hydroxide. Aluminum is a metal. It is a representative metal. So notice that we don't see the charge in Roman numerals, or else we know it's a transition metal. So aluminum has a 3+ charge. Looking at my periodic table, it's group 3A. Hydroxide is a polyatomic ion. It's probably one of the hardest ones to recognize that it is a polyatomic ion because it doesn't have an 8 or ite ending that kind of signals to us that you have a polyatomic ion. But hydroxide is OH with a -1 charge. So this is acting as an entire unit. Not going to split it up. That whole thing, O and H together, have a -1 charge. Now that I've written this, the next step is to drop and swap. So I have Al1, I'm not going to write that, and I have 3 hydroxides, so I need parentheses, and I'm going to drop that 3 outside the parentheses because that says I have 3 of whatever's inside the parentheses. I have 3 OHs, OH, OH, OH. Double checking our math, you have 1 aluminum with a +3 charge, that is +3, and you have 3 hydroxides with a -1 charge each, that's -3. So this will sum to 0. Yes, we've done it correctly. All right, what you're looking at is the dessert menu in my home. Just kidding. Wait till you get old. You're going to be having antacids all the time. Let's talk about antacids. Antacids, the active ingredients for a lot of these are both ionic compounds and ionic compounds with polyatomic ions. So let's start with Tums. The active ingredient in Tums is calcium carbonate. Okay, so calcium's our representative metal and carbonate is a polyatomic ion. It's +2 -2, which is why it's a 1-to-1 ratio for each other. Malox has an active ingredient of magnesium hydroxide. If you're wondering where I came up with these formulas so fast, magnesium has a +2 charge, hydroxide has a -1. We dropped, swapped, added parentheses. One thing that's not on here that I also kind of want to talk about is iron 2 sulfate. Iron 2 sulfate is also known as ferric sulfate, and they use ferric and ferrous in medicine a lot. You would see this if you had a patient who had anemia and was needing extra iron as a supplemental vitamin or a supplemental pill. They would need to take ferrous or ferric sulfate depending on which of the charges that they have. So we see polyatomic ions a lot in medicine as well. This is one of the fun uses of another ionic compound that has a polyatomic ion in it. If we would like to see how your digestive tract is working, we're going to have you drink something that is a very thick, disgusting drink that has an active ingredient that has barium sulfate in it. And when you drink the barium sulfate, you can start to take x-rays. Barium sulfate is fairly dense, and so it shows up really nicely on an x-ray. And you drink the barium sulfate, and they'll take pictures periodically, and you can see the barium sulfate travel down into the stomach. And sometimes what they're looking for is how long does it take the stomach to empty? How long does it take the barium sulfate to enter the small intestine and the large intestine? And we can actually visualize when you have a blockage in the small intestine or the large intestine. So if you have constipation, or I don't know what else would be a blockage in there. I'm not going to spend time imagining that right now, but great way to visualize, and it's a non-radioisotope as well. So we're looking at normal bone on the left versus osteoporotic bone on the right. So osteoporosis results in a decrease in bone density. This is something that tends to happen as people age. When you have a decrease in bone density, bones tend to become more brittle, they're easily fractured, so this can be very problematic. So bone is mostly the ionic solid hydroxyl apatite, and that is the structure that or the formula that you're seeing up here. You don't have to have that memorized. This is kind of just an interesting aside. So hydroxyl apatite is the ionic solid. Again, this doesn't follow the basic ionic compound rules that we have for polyatomic ions. The structure is actually a lot more complex. This is more of an OChem or an IChem type of conversation, but it is an ionic compound, and this is constantly broken down and it's rebuilt within the body. And women specifically, as they age, the rate of bone loss is often greater than the rate of bone synthesis, and so it results in osteoporosis. So you have brittle bones that are not as dense anymore.